Hello, IB. We are going to get started into chapter 13 and start to look at how all of this information that we've learned now with vectors applies to some real life situations. We start off this opening problem, beginning of chapter 13, with a yacht club that is situated at 0, 0, and you have a yacht that is passing the yacht club. So at 12 o'clock noon, the location of it is at 2:20 on this coordinate grid. And then after 1 hour passes, so at 1 p.m., the yacht is now at 6:17, so right here at this location. And then at 2 o'clock, it's at 10:14 at this location. So already we can notice that the yacht is traveling in a linear motion, with linear motion, so in a linear direction. And what we're noticing with the path of travel is that we are moving 4 units in the positive x direction, so +4, and we're moving down 3 units, so -3, in the negative y direction. And just so we can prove that this is linear motion, it happens again over that second hour, +4, -3. So already we have this idea of a starting location and then a change in the x and the y direction. And already this should hopefully be triggering some memories of a linear equation where your plus b is your original point and then your m is your gradient, so your change in the y and the x direction. But now when we're using vectors, we can use vectors to identify the starting position and the position after time passes and also the direction that we're moving. So find the position vectors of A, B1, and B2. Well, the position vector of A from 0, 0 to A, so if you think about a straight line going from 0, 0 to A, you're already showing that your position vector is at 2:20 because it's going to be the same as that coordinate. For B1, that's after 1 hour of passing time, we've been told that you're at 6:17, and that is also your vector for B1, the position vector. And then the same thing for B2, the position vector would be at 10:14. And then it says explain or find A to B1, explain what it means. So if I'm moving from A to B1, we know that we subtract where we terminate off from where we originate. So moving from 2 to 6, that's 6 minus 2, which is a change of 4 in that x direction, and then 17 minus 20 is that -3. So that's just verifying that we actually do change 4 units to the right in the x direction and 3 units in the negative y direction. If you actually want to find how far the yacht travels in 1 hour, you're looking at this distance here. So we want to find the magnitude of that vector. So if we want to find the magnitude of vector A to B1, we can take the square root of A to B1, so 4 squared is 16, -3 squared is 9, so that's the square root of 25, which gives you 5 kilometers, since we're talking about kilometers in this map. And notice that we're traveling 5 kilometers between 12 o'clock and 1 o'clock. So for our speed, we can describe it as 5 kilometers per hour. And then we can continue to start thinking about, well, what does this mean for us with this linear motion? If we find A to B2, or A to B3, or A to B4, notice what's happening every time that we just let 1 additional hour pass. So every time we let 1 additional hour pass, we're just going to continue to move 4 units in the x direction and 3 units in the negative y direction. So if you start to think of this linear equation that we were thinking of earlier, you have this 4 and -3 multiplying by every unit of time. And we started at an initial point of 2. So let's start at 2:20. And then for every unit of time that passes, let's multiply the x by 4 and the y by -3, and then we'll have our new location along the line. And this could occur for as many hours as we allow to pass. So if you're thinking of, well, what's then represented by the vector O to B2, from O to B2, what would that actually tell us about this yacht? All right, so think about what you would say if you were going to answer that question. So just trying to go through what we're linking here with our linear motion and also how vectors play a role in that. And we'll start by just commenting on this opening problem in class as well. So now getting into chapter 13 and section A, we are limited on the amount of questions that we have to practice this, so we'll just go through a couple examples in the video. But it is an interesting idea to think of what outside factors wind up affecting motion. So for example, if you have a boat or a plane and they are moving in a certain direction, you've got these wind that could affect the direction and the speed of the plane. For boats, it could be wind, it could be the water, the waves, all of that's going to affect it. So you've got here wind speed at 10 knots, moving in this south direction, coming straight from the north. And then you've got this boat that's trying to travel in this direction. And what winds up happening is you basically have this opposing, the relative wind that's actually going to slow the boat down and also change the direction. So all of these external factors are going to affect whatever particle we're watching or following their motion. So what we'll take a look at next is just an example of a swimmer who's trying to cross a canal and has some current affecting the swim. So Mary is standing at point P, and she's trying to cross the canal to get to point Q. She's able to swim at 1.2 meters per second. So if we had absolutely no factors that were affecting her swim, she could swim straight across from P to Q, and she could swim at about 1.2 meters per second. All right. However, the water is flowing to the right at a constant speed of 0.6 meters per second. So she has this external factor, this force from the current that is pushing to the right at 0.6 meters per second. So ultimately, if she doesn't actually change her course when she begins from point P, she's going to start to move in this direction here, okay? And then she wouldn't actually get to point Q. So if Mary tries to swim directly from point P to point Q without allowing for the current, what will her actual velocity be? So we have this velocity vector that's in red here. That's actually representing what she's doing. So she has the direction, which is pointing kind of in this southeasterly direction, and then the magnitude of this vector is actually going to tell us what her velocity is or what her speed is, since we have the direction already. So what we'll wind up doing is we'll take 1.2 squared plus 0.6 squared as our x and our y component, and then take the square root to figure out what the magnitude of this vector actually is, since that's actually what's affecting it. So we wind up taking 0.6 squared plus 1.2 squared, and that will give us whatever our velocity is. Excuse me. So for our velocity, we'll wind up with, let me come down here just so we have a little bit more space. Velocity is going to wind up at 1.34 meters per second. So there, she does wind up being taken off course quite a bit there. So her velocity is 1.34 meters per second, and that's actually what would wind up happening if she was pushed toward the right and not accounting for that current. So in part B, and we'll look specifically at I first, Mary wants to swim directly across the canal to point Q. At what angle should she aim to swim in order that the current corrects her direction? So if she actually winds up swimming and compensating for the current, she's going to take off in this direction here at 1.2 meters per second. And the current will still wind up affecting her swim and pull her back this direction at 0.6 meters per second. And then that'll correct her swim and she can actually swim straight toward point Q. So in this situation, since she's compensating for moving in this additional angle toward the right from her starting point, that's actually, her swimming speed is 1.2 meters per second. So that's how fast she's going to swim. And then we've got this x direction being affected. So then her straight direction moving across from P to Q is actually what we're going to find here as her new velocity vector. So at what angle should she aim to swim in order that the current corrects her position? This is the angle that we want to find. So since we're dealing with an opposite to that angle theta and a hypotenuse, we can use sine theta and set that up as 0.6 over 1.2, and then use inverse sine to find our theta. So 0.6 and 1.2 just reduces down to 1/2. So sine at 30 degrees will give us 1/2. So she'll need to take off at a 30-degree angle in order for the current to correct her direction and for her to move straight across from P to Q. So to finish up part 2 of this question, we want to know what her actual speed will be then. So if she's swimming at 1.2 meters per second, but the current is affecting that, then what is this new velocity vector? So notice we have the hypotenuse, we have the x direction, we're missing this vertical direction here. So we are going to set it up as 1.2 squared this time is equal to 0.6 squared plus whatever her actual velocity squared is. So now if we manipulate this one, for her new velocity, we should get 1.08, and that's in meters per second as well. All right. So if she does compensate it and she swims straight, notice she is swimming a bit faster than 1.08 meters per second. Oh, a little bit slower there. Since she is only able to cover that 1.08, so a little bit over a meter per second. So notice how that does affect her swimming speed since she's overcompensating for that one, for the current. All right, guys, let's take a look at one more example before we leave you on your own. All right, guys, for this next example, question 4, I'm going to set you up with a couple hints so that you can try to work through each of the sections on your own, and we can start with this as a conversation next class. So similar to the last one, you're swimming across a river, and Stephanie swims at 1.8 meters per second in still water, but you have a current that's flowing to the right at 0.3 meters per second. First, we want to just find the distance from x to y. So automatically, we're knowing that we recognize this as a right triangle. We're given this as a right triangle as well. It's directly across the river. So we can use, we know the river is 80 meters across, and this distance is 20. So we should be able to find the distance pretty easily using Pythagoras. For part B, in which direction should Stephanie aim so that the current will push her onto a path directly towards y? We know we want her to go from x to y, but because the current is pushing her to the right at 0.3 meters per second, what Stephanie is going to have to do is compensate for that, since what's happening to her path is there's a vector pushing her at 0.3 meters per second toward the right. So there's this additional angle that she should wind up starting to swim at so that she gets pushed back toward y, and that way can actually get to y, similar to the last example. So what we want to find is in which direction, meaning at what angle does she actually need to leave at in order to compensate? So what direction does she need to head toward? So if we could find this angle that's right here between her direct distance from x to y and then also what she's compensating for, then we would be able to answer this question. So for part B, we'll have to use our knowledge of right triangles because we have a couple sides of a right triangle. We also have a non-right triangle in here, if you just look at the green and the red triangle, and possibly sine or cosine rule could help you out here. So we're looking at, do we need to just use Pythagoras? Do we need to bring in the sine rule? Do we need to bring in the cosine rule? So take a look at that diagram and see what we might need in order to figure out that angle. And then once we have that angle, how do we find the time that it will take her to actually cross the river? All right. So these three, go ahead and start thinking, try to at least set up A and B, start thinking about C, and then we'll start with this next class. Have a good night.